Assalamu alaikum. My name is Armagan Anjum. I am a research officer from Department of Orthotics and Prosthetics, Government College University, Faisalabad. Today I am going to discuss about how to calculate RPM. So let's get started with this video.
Hi everyone. Today I'd like to talk about the RPM of machines and specifically how to calculate what your RPM should be. There's a lot of people out there, and some of whom have been in the trade for a long time, that believe that any RPM works for any material, and that's not the case. Your material and the diameter of your material impact what your RPM should be. So I've got two pieces of aluminum here. One of them is larger than the other one. And when we talk about RPM, the critical thing in figuring out what your RPM should be is what is called surface feet per minute, and that is your cutting speed. So what that is on the lathe, it would be how many feet of circumference of the material is moving past your cutter in 1 minute, or on the mill, it would be how many feet of cutter is moving past your material. The larger of the two pieces would have to run at a slower RPM because it has a larger circumference, so you have more feet of material moving past the cutter in 1 minute. Whereas our smaller piece, if we put our lathe bit there, this would have to move at a faster RPM because you've got less circumference and less surface feet. Now, depending on what your material is as well, your cutting speed is going to change. If you have a soft, easy-to-machine material like aluminum, you can run that at a higher cutting speed than you could if you had a hard steel. These are the numbers I recommend to my students at Parkland College, and these are based on using a high-speed steel tool, so either a high-speed steel lathe tool or an end mill or a high-speed steel drill. Mild steel is basically anything that's not hardened, so your 1018 steel, your cheese steel from the hardware store, black pipe, tubing, things like that. Tool steel is anything that is already hardened or hardenable. So I would use this for anything from 4140, which is a very tough steel, up to any of the drill rods, die steels, and things like that. Mystery steel kind of goes hand in hand with that, because if you just pull something out of the scrap bin and you're not entirely sure what the alloy is, it could very easily be a hardened steel, and you don't want to burn up your tool by running it at mild steel speeds when it's actually a hardened steel. The aluminum and brass speed is very conservative, and the reason for that is if you're running something super fast, then it decreases your reaction time in case there's a problem. So these are the speeds that I use for my students there at Parkland College, and I try to get them to be as conservative as possible with their speeds, partly so their tool lasts the entire semester, but also so they don't crash the machines. Now, you may not have to machine a ton of bronze, but I actually machine it quite a lot. And bronze is a lot harder than brass. It looks like brass, but it's really not. It is a beautiful material to machine. I mean, you have to work really hard to get a bad surface finish with bronze, but it's a lot harder than brass. And then stainless steel, I like to run at 40. Stainless is not necessarily hard. It's actually just that it doesn't conduct heat very well. So if you let the tool rub or you run it too fast, it has a tendency to harden locally in the spots where the tool is rubbing. So for that reason, you really want to run stainless quite a bit slower than even tool steel. Now, these are actually very conservative numbers, which is by design. If you're running at these speeds, you're not going to destroy your tool with heat. As I mentioned before, these numbers are based on using a high-speed steel tool. So if you were using a carbide tool, you can actually double or triple these depending on whether or not you're using coolant. Another thing that you might find is you might look up cutting speeds for different materials and find charts that are wildly higher than these on the internet. And those are usually found from manufacturers of cutting tools. Well, those are production-oriented numbers. So those are actually based on a 15-minute tool life, meaning that at that speed, that corner of that insert should last 15 minutes before you have to flip it to a fresh corner. Obviously, in the home shop world and in non-production shops, that's not really a consideration, whereas tool life might be. So how do we turn our SFM chart into the RPM of the machine? Well, we have to use math. Here's our equation. Our revolutions per minute will equal our surface feet per minute, and that's dependent on your material, times 3.82. That's a constant. I'll talk about that in a second. And then divide that by the diameter. The diameter is going to be the size of the cutter or the hole you're boring on the mill, and it will be the size of the stock usually on the lathe unless you're drilling a hole. That's the big exception there. If you're drilling or boring a hole, it's going to be the size of the hole because you're concerned about how many feet are moving past the drill or the boring bar in a minute. The outside is irrelevant. So where does 3.82 come from? Well, 3.82 is actually 12 divided by pi. So what we're doing is converting our surface feet into surface inches because the diameter that we're going to be dividing by is in inches. Now if you're going to be programming a CNC machine, you use this formula because you can specify the exact RPM of the spindle in the program. So you want to definitely use 3.82. However, if you're working with manual machines, you can simplify your math and just make it SFM times 4 divided by diameter. The 4 is an approximation of 3.82, and in the case of manual machines, you're very rarely ever going to be able to choose the calculated RPM. You're always going to end up choosing one that's close to it, but it's not going to be exactly right. So 4 actually gets us in the ballpark, and it's a whole lot easier to remember. So for my students there at Parkland College, this is the formula that I want you guys to use. Now in those cases where your calculated RPM is one thing and you don't have the exact option, you want to follow Price is Right rules. That means you're going to choose the closest one without going over your calculated RPM. So if you calculate your RPM at 1440 RPM and you have a choice between 1115 and 1750, you want to choose the lower of the two. You want to choose the 1115 because if you run it at 1750, you're actually machining at a much higher SFM and you might burn up your tool. So let's do some samples. Let's say that we're using a 3/8 diameter end mill and a piece of aluminum in the mill. The cutting speed of aluminum, according to my chart there, is 150 SFM times 4 divided by our diameter, which I said was 3/8, so that would be 0.375. Got to use decimal inches here. We do 150 times 4, that's 600, divided by 0.375, and we end up with 1600 RPM. Now, of course, you would then go ahead and choose whichever speed option you have that's close to that, but without going over. So how's about if we're turning a piece of mild steel in the lathe and it's 5/16 in diameter? So mild steel's SFM is 90 times 4 divided by 5/16, which is 0.3125. So if we do that on our calculator, 90 times 4 equals that, divided by 0.3125, and we get 1152 RPM. Now what if we were drilling a hole in the end of a big piece? So let's say we had a 1/4 inch hole in the end of a 6-inch diameter piece of stainless steel. So stainless steel's SFM is 40 times 4. And then which of those two diameters are we going to use? It's a 1/4 inch hole, but it's a 6-inch piece of stainless. If we're drilling a hole, we need to use the size of the drill because that's what our material is moving past. So in this case, it has to be 0.25 down here. 40 times 4 divided by 0.25, and we get 640 RPM. Now don't worry, metric folks, I haven't forgotten you. There is a formula for you guys too. Your cutting speed is expressed in meters per minute, and the diameter is going to be given in millimeters. So your RPM is going to be equal to 1,000 times the meters per minute divided by pi times the diameter. So 1,000 times the meters per minute is basically giving you millimeters per minute. And remember, your diameter is going to be based in millimeters. So how does that actually affect your cutting speed? You can take my SFM numbers from before and divide them by 3.3 to get your meters per minute. That's a nice approximation, gets you pretty close. So these are those numbers converted into metric for you. So 27 for mild steel, 15 for tool steel and mystery steel, 45 for aluminum and brass, 30 for bronze, and stainless steel is 12. So can the RPM be too low? The answer is definitely yes. I mean, especially with a carbide tool, they aren't as sharp as high-speed steel tools. So if your RPM is too low, it will tend to kind of plow off material and tear it more than cut it. The big area where the RPM can be too low, though, is with small drills. If you're drilling at too low of an RPM, especially with small drills, the drill can get overloaded because you're feeding proportionally faster to the RPM, and the drill tends to snap. Small drills are already fragile and easily broken, and the breaking problem is just compounded by the fact that most manual machines can't run fast enough to actually cut at the proper SFM for those small drills.
RPM calculations. RPM is the abbreviated form of revolutions per minute, which is the amount of time the tool or the workpiece rotates in 1 minute. As we know, in lathe machine, the tool is stationary while the workpiece is rotating. So the RPM of a lathe machine will be the amount of time the workpiece rotates in 1 minute. There are two factors that must be considered when determining the correct RPM. The first one is the diameter of workpiece being used or the tool being used. For example, if a drill bit is used, then it will be the size of drill bit. On the other hand, if a round shaft is being machined, then it will be the diameter of shaft. The second factor is the type of material that is being machined, whether it is easy to machine material or difficult to machine material. The reference chart is attached. Now the question arises, what will happen if RPM is too slow or too fast? Using an RPM that is too slow will cause unnecessary pressure and wear on the tool. This low RPM will mean that the drilling pressure will be too much and the drill bit will probably break. While if the RPM is too fast, it will cause a great deal of chatter and vibration on both the workpiece and the tool. Moreover, the heat generated from this fast RPM will damage the cutting edge of the tool. Now how to calculate RPM. RPM is calculated by the following formula: 4 into CS, that is cutting speed, divided by the diameter. 4 is the given value of the formula, so it doesn't change. CS is the cutting speed of the specific material and it will change as the material changes. Diameter is the diameter of the workpiece or the tool being used. The cutting speed is defined as the rate at which a point on the work circumference travels past the cutting tool in 1 minute, or simply it can be said that workpiece removed by the cutting tool in 1 minute. Cutting speed is expressed in either feet per minute or meters per minute. For our purposes, and because most of the industry use empirical system, we will be using feet per minute. The cutting speed of some of the material in feet per minute is given in this table. For example, the cutting speed of machine steel is 100, tool steel is 70, cast iron is 60, bronze is 90, while the cutting speed of aluminum is 200. These cutting speeds are based on cutting tool made up of a material called high-speed steel. But if the tools are made up of carbide, which is a much harder and durable material, then the final answer will be multiplied by 4. For understanding, a sample question is given. The question states that calculate the RPM when parallel turning a 2.5 inches diameter piece of tool steel. The RPM is calculated by the following formula: 4 multiplied by CS divided by diameter. 4 is a constant, 70 is the cutting speed of tool steel, while 2.5 is the diameter. By calculating the values, the RPM came out to be 112. So the RPM will be 112 for 2.5 diameter piece of tool steel. But if the question stated that carbide tooling is used, then the answer will be multiplied by 4. So the answer will be 448 for the carbide tooling. Given below are the questions which you will be able to solve by yourself. But if you find any difficulty, feel free to contact.